Welcome to This Explainer. Today, we're embarking on what is, honestly, a thrilling detective story. We're going to look at how geomorphologists, the scientists who study the physical features of the Earth's surface, use an incredibly specialized toolkit to measure the constant hidden movements of our planet. From literal microscopic grains of sand all the way up to massive shifting tectonic plates, we're going to unpack exactly how we decode Earth's dynamic mysteries. I absolutely love starting with this classic quote from Isaac Newton. It perfectly captures that profound sense of awe and inquisitive discovery that drives this entire field. In a way, we're all just standing on the seashore, surrounded by the immense mysteries of the Earth's surface. But unlike Newton's time, today we actually have the technological tools to sail out into those great oceans of truth. So here's our roadmap for today. We're going to hit the dynamic Earth, look at measuring water in motion, talk about dating the deep past, reading deep-sea sediments, shorelines and tectonic shifts, and finally wrap up with the future of geography. Let's dive in. Starting off with Section 1, the dynamic Earth, or as I like to think of it, the global crime scene. To actually investigate this shifting landscape, we first have to define the terrain mathematically. And that brings us to geomorphometry, which is the measurement of a continuous rough surface. Now, in plain English, it just means we treat the Earth's surface like a giant 3D digital grid. By smartly ignoring complicated anomalies like deep caves or weird overhangs, we can isolate and calculate the landscape's features so we can, actually measure them. It's the crucial first step. Moving right along to Section 2, measuring water in motion, specifically rivers and surf zones. Have you ever wondered how on Earth we track and measure something as chaotic as flowing river water or the brutal energy of a crashing wave? Well, we actually look at the sediment it carries using the electrical sensing zone method, commonly known as the Coulter counter. The genius here is really in the step-by-step process. You suspend sediment particles in an electrically charged liquid, an electrolyte. As they're forced through a tiny hole, each little particle displaces its own volume of that liquid. This briefly changes the electrical resistance in the circuit, and the size of that resistance spike, it's exactly proportional to the volume of the particle. It's just a remarkably elegant way to count and measure microscopic sediment in moving water. Now, obviously, we use physical current meters with little propellers to gauge water speed, but we also rely heavily on mathematical models like the Manning formula. This calculates river velocity by factoring in the hydraulic radius, which is basically just how deep and wide the water is, the slope, and a roughness coefficient, which is exactly what it sounds like, how bumpy the riverbed is. This formula lets us tame the chaos of rushing water into predictable data, which is absolutely vital when we need to predict devastating floods. All right, Section 3, dating the deep past. This is all about reading time itself. Figuring out what happened is really only half the battle. We desperately need to know when. Enter radiocarbon dating. Pioneered by W.F. Libby back in the late 1940s, this is how we read deep time. But to use this tool, Libby noted that 3 absolutely crucial assumptions must remain true. We have to assume the biospheric carbon reservoir is in balance, that cosmic ray influx from space hasn't wildly fluctuated, and that the sample's carbon hasn't been contaminated since it was buried. When these conditions are met, boom, we have a biological clock that ticks back thousands of years. But hey, what if you're dating rocks or sediment, not organic matter? That's where 2 fascinating techniques come in: thermoluminescence, or TL, and electron spin resonance, ESR. Both of these methods treat mineral grains like tiny, natural batteries that charge up with background radiation over time. TL measures this by heating the grain until it releases all those trapped electrons as a flash of light, acting as a natural dosimeter. ESR is similar, but it measures specific levels of trapped electrons magnetically. The real game changer here? ESR is completely non-destructive, meaning the sample remains entirely intact for future study. No way, right? It's brilliant. Let's plunge into Section 4, reading deep-sea sediments, the Earth's long-term climate record. Way down in the dark of the ocean floor, stable isotopes are literally acting like an undisturbed ledger for the Earth's climatic history. Deep-sea sediment cores show the cyclic variation of oxygen-18 isotopes, which get trapped in the shells of these microscopic sea creatures called foraminifera. Because the ratio of oxygen isotopes they absorbed is directly controlled by the seawater's temperature and the glacial ice volume at the time they lived, reading these sediment cores reveals cyclic climate fluctuations spanning over 1 million years. It's a flawless, natural record of our planet's ice ages, and analyzing it is absolutely essential for understanding modern climate change. Next up, Section 5, Shorelines and Tectonic Shifts. We are talking massive planetary movements now. Believe it or not, the land beneath our feet is surprisingly elastic. Take Scotland, for example. During the last ice age, the immense weight of glaciers literally pushed the Earth's crust down. When the ice finally melted, the land began to slowly bounce back up. By mapping ancient shorelines that now sit way high above modern sea levels, researchers can track this process called isostatic rebound. This allows us to visually prove and calculate these massive tectonic shifts. So what's actually driving all these massive shifts on a global scale? Well, conventional current theory points right to convection currents deep within the Earth's mantle. This intense, boiling heat cycle drives seafloor spreading, acting like a giant geological conveyor belt that constantly creates new crust and pushes the tectonic plates apart. And our modern precision in measuring this spreading is just staggering. By bouncing lasers off retroreflectors left on the moon by the Apollo missions, scientists can measure the incredibly slow, grinding motion of these plates down to an accuracy of just 1 centimeter per year. Think about that. We are literally using the moon as a yardstick to measure the Earth's spreading seafloor. Finally, let's look ahead to Section 6, the future of geography and uncharted territories. As our measuring capabilities expand, from simple surveyor tools to those crazy lunar lasers we just talked about, the discipline itself has to constantly evaluate its own terms of reference. Geography is characterized by continuous debate, keeping pace not just with new tech, but with pressing human concerns and global environmental shifts. Ultimately, these advanced tools are only as good as the human insights driving them. You know, academic disciplines aren't just dusty, abstract rules. They're human creations that are constantly being reshaped. This incredible geomorphological toolkit isn't just about counting grains of sand, it's about our survival. We track these hidden mechanisms and shifting plates so we can predict devastating earthquakes, prepare for rising sea levels, and ultimately protect our communities. I'm going to leave you with this thought to ponder. As our toolkit grows ever more precise, from counting microscopic grains to tracking seafloor spreading from space, how many more of Newton's great oceans of truth are we on the brink of discovering? What hidden planetary mechanism will we uncover next? Thank you so much for joining me on this explainer, and keep questioning the ground beneath your feet.